Okay, hi everyone, thanks. So I'm going to talk to this topic of interference from other things on the moon once we start building radio telescopes on the moon. And I'm going to present a little bit of work that was the honors thesis of an undergrad here at ASU, Jake Trenter. So as you know, the motivation for going to the moon is that many science cases want low-frequency radio observations. And on Earth, the Earth's ionosphere becomes very complicated to see through when you start getting around 50 megahertz and lower, and becomes generally opaque, kind of below 20 or 10 megahertz. It varies. So there's a good motivation to put radio telescopes off the Earth. But once you do that, you start to be able to see all of the transmitters that are on Earth, and the sort of tens of megahertz frequency band is a very active and used band for communications on Earth, TV stations, radio stations, other types of communication. And so the whole motivation for the far side of the moon is that the moon is a great, huge attenuator, and you can put your telescope on the far side of the moon, and the moon attenuates. It's as good as being at Neptune compared to being like on the front of the moon. And so the problem becomes that you need infrastructure to be able to do your science on the far side, and you need the orbital assets that might communicate your data back to the Earth, and you expect that there will be, of course, many other users of the moon and human exploration and other science investigations going on. And so you want to make sure that you haven't gone to the effort to put your radio telescope in what should be a quiet place, but other things like lunar orbiters will be causing too many problems. And so this is a bit of analysis to show that things should be quite reasonable and hopefully manageable with some coordination. So on the right is just a quick plot of that Neil Bassett made out of University of Colorado, showing the sort of attenuation on the far side of the moon there, and that little black kind of wake. If you're wondering what the radio sky looks like, here's an image made by the Owens Valley long wavelength array out of Caltech, and it's showing false color of the radio sky ranging from about 30 megahertz to about 80 megahertz. And all the little dots you see on this aren't stars, they're galaxies emitting radio. And the hazy stuff you see along the plane and kind of going off of it is synchrotron emission from our own galaxy. And so it's very strong. And we really want to see if any orbital assets around the moon that might be leaking radio emission are going to be, brighter than this, weaker than this. This is sort of the reference that the telescopes already have to deal with. And so if you can keep unintended electromagnetic leakage to this level, is hopefully not a problem. And so just to put some numbers to this, you can see on the right here, the brightest sources in radio astronomy units are about 100 to 1,000 Janskis. And if you're not familiar with that unit, it's right there. I'm kind of in the bottom right of that top box. It's a flux density, so it's flux per unit frequency. And you can see the 10 to the minus 26 factor in the front, so it's quite small. The faintest sources that we typically see with radio telescopes would be of order of millijansky at these frequencies. And sort of this haze of the galactic background would be of order half a Jansky on the sort of resolution of these types of maps. We're looking at probably going to lower frequencies than this 150 megahertz data here, but it scales not too steeply. It'll be brighter. These sources get a little bit brighter at lower frequencies, but these numbers are still a good ballpark number. And the bottom plot's just showing an example of where the counts of radio sources have been cataloged. So if you just kind of look at the x-axis, it shows the range of frequencies and the range of fluxes and Janskis that are kind of relevant. So what does the situation look like on Earth? Do satellites orbiting Earth leak radio waves? And the answer is yes. And here's two examples recently out of the LOFAR teams.
Hi, Judd, can you hear me?
Plot.
So sorry to interrupt. Okay? We lost you for the last minute. Do you mind going back a couple slides and continuing?
Okay. Do you see, is this where you got me here?
Yes.
Okay. And did you catch all of this slide?
We got the point.
I believe so, yeah.
Okay.
We got the point up until where you said if the unintended emissions are less than this, it's fine.
Okay, that's good enough, right?
Thanks.
And then some numbers for context.
Yeah,
let me know if
we heard about you talking about the unit, the Yankees.
Okay, yeah. So what we're hoping is that any satellite leakage will be at or below sort of the numbers on this top right box here, because that's sort of the typical sky brightness. Okay. And so then the next step was, does do satellites orbiting Earth leak radio waves? And the answer is yes. And so there's one example here. The plot on the left is from Starlink, is of a Starlink satellite, and it's time on the x-axis and frequency on the y-axis. And you see the little lit up area kind of at time 0 when the Starlink satellite went through a beam of this telescope. And there's a number of Starlink satellites, all right? It's a huge constellation, and some are quite quiet and some are not. And the range of sort of fluxes that have been observed, as you can see on the left, 2 to 1400 Janskis. And that's for satellites orbiting at around 500 kilometers in low Earth orbit. The other type of sort of radio interference we get from satellites is when they scatter radiation from transmitters on the ground. And so you can think of the satellite there as kind of like a mirror, and it just happens to scatter radio waves that hit it and come back. And the ISS, the International Space Station, is an example of that happening. And here's a plot of that on the right. And that, in some circumstances, can reach, has been observed at sort of equivalent of 40 Janskis, so comparable to a bright source in the sky. What we did for our modeling for the moon was take a notional case of Gateway, the planned space station that could orbit the moon, and we imagined some of these transmitters and some of these effects happening from Gateway. And so we took the orbit that Gateway has been, the reference orbit for Gateway, which is a near rectilinear halo orbit, and you can see some examples of that. It's a very elliptical orbit that's been the reference orbit. And if you're wondering, like me and if you're an astronomer, you don't know much about orbits, the reason it's called near rectilinear is because when you plot it in the Earth-centric frame, you get these sort of right angle type dips as it comes past the moon. So we're going to take that orbit and have a look at it first. And here is some histograms summarizing what a telescope on the far side of the moon, where it would see the Gateway space station. And so this is sort of near where Stuart was just talking about for Lucy Knight. We put it right on the equator on the far side of the moon, dead center. And the good news is the halo, or the Gateway orbit, is quite distant generally from the moon. It ranges from about 3,000 kilometers to 10,000. And if you're near the equator on the far side, it never gets too high in the sky. So you can see this elevation angle stays kind of low along the horizon over here. So what happens if you want to imagine that Gateway is emitting radio waves? We had to guess. We don't know what it's going to be. There are no real strict limits for satellites. So if you take FCC Class A radiated emissions limits, which is for consumer devices, which of course Gateway will have some on it. There are some numbers here that the numbers probably aren't too critical. And if you compare them to what's been observed for some of the Starlink satellites, down here on this bottom plot is showing some of these same field strengths, and this red dotted line is showing where they would stand. And then these are cumulative distributions for Starlink satellites, how strong they're emitting. And so it kind of falls right in the middle of the range that Starlink satellites have been observed to emit at a couple different frequencies, so it's a good reference. And if you put that on Gateway and you see what it would look like to your telescope, you find that typically Gateway is going to look like a source of 10 to the minus 3 Janskis or a millijanskis, so like some of the faintest astronomical sources we're expecting. The other thing is will Gateway scatter radio emissions and be too strong that way? And so if you take a toy model of transmitters on the Earth and you imagine that they're just transmitting every which way and they bounce off Gateway and that comes back and hits and gets reflected to your telescope on the far side of the moon, you can use the radar equation and you can see it goes like distances squared. So distance from Gateway to the Earth squared and distance from Gateway to the moon squared. You plug in some numbers and some numbers you kind of have to guess, like the cross-sectional area of Gateway. And you find out that any one transmitter, and this is a bright transmitter like an FM station, will be quite faint if it's scattered from Gateway to your telescope, 10 to the minus 7 Janskis, so well below the typical sources we expect. And so the problem is there's many transmitters on Earth, lots of TV stations, lots of radio stations, other things going on. And so you imagine lots of transmitters in doing this, and you might multiply by the number of transmitters. So here's a great plot from a paper from the 70s where they counted up how many TV stations were visible to any line of sight in space. They were looking from a particular star. And as a function of time, as the Earth spins, you see the number of TV stations visible goes from like 0 to 80. And so there's going to be a diurnal kind of pattern to that. So you multiply by 100 and you get sort of millijansky contribution from Gateway reflecting Earth transmitters. So just to start to summarize here, you put this all on one plot and compare it to one of our concepts for a telescope that we would like to build in the future on the moon. So here's sort of how bright we think Starlink would look like if it were at the distances that Gateway will be. Here's if Gateway were emitting that particular FCC limit we modeled, and here's if Gateway scattering the Earth transmitters. And you compare that to how sensitive the telescope will be, and most of these sources will be, most of the Gateway will be visible in a minute. Some of these scattered things you might eventually see from Gateway if you integrated for an hour. And the sort of targets you're looking at are down kind of off the bottom of this plot. So the moral of the story is orbital assets will be noticeable. They'll be visible as sort of moving radio sources in the sky, but they should be generally comparable to the astronomical sources. So that's good news. We have lots of techniques from Earth to handle those types of interferers, but it does make the science harder, especially some of the very demanding science that Stephen talked about and Evetta will talk about. So we don't want this to be kind of a forget about it message, but we definitely want to maintain, some sort of coordination and management to make sure that the orbital assets that do go to the moon aren't wildly different than the sort of things we're seeing in low Earth orbit. So that's it. Thank you very much.